The next section will be about real and reactive power control. When a machine is connected to an infinite bus, its speed and terminal voltage are fixed. We have ever two controllable variables, the field current and the mechanical torque on the shaft. Let's look at an alternator with a leading power factor lagging. That will be the current and the terminal voltage. IAXS cos phi. That is the induced EMF. Now if we have a constant power, that will be the loci of IA cos phi, which is this value here, IA cos phi. For a constant power, that will remain the same. If we now, let's say we have a unity power factor, which means it will be that value, then that will be IAXS, and that is the induced EMF and the load angle delta. We can now ever change to a leading power factor as well. So that the current now lies there with the leading power factor phi. IAXS is going to be that way, and the induced EMF will be there. So from this can be seen that for an overexcited alternator with a lagging power factor, E is bigger than V, and for a leading, E is less than V, and it is said to be underexcited. This machine will deliver power to the system, and this one will receive it, the power from the system. Now if we look at the reactive power, S is equal to P plus or minus JQ, and therefore P will be VIA cos phi, and Q will be VIA sin phi. Now if we look at our equation, E angle delta is V plus IAZS angle beta plus or minus phi. We can say that E angle delta minus V angle 0 divided by ZS angle beta is equal to the current IA at an angle of phi. If we break that up, we have E angle delta divided by ZS angle beta, and V angle 0 Z angle beta. Now if we draw a partial phasor diagram, we will have V there, E leading by a certain angle delta. Now if both of them is divided by beta, we will have E over Z, and this will be angle beta. The same will happen to B. That will be V over Z. Then this will be angle beta, and the angle between those two remains delta. So now if we want to determine the developed power, that has got to do with E and the current. So therefore it will be E, and if we look at our phasor diagram, at any point if we move in this direction, we start at E. The first part that we get to is E over Z, and the angle between E and E over Z is cos of beta minus V over Z, which will be cos of, let's look at another color there, that beta there plus delta. That gives us a formula of E squared over Z cos beta minus EV over Z cos beta plus delta. If we want to determine the output, that has got to do with the voltage, and therefore we have V, and then the first part that we get when we go around will be E over Z, and the angle between them will be cos beta minus delta, and minus the next part will be V over Z cos beta. And reactive power Q will be EI sine phi, where this was EI cos phi. So therefore this will become E squared over Z, sine beta minus EV over Z sine beta plus delta. And the output power Q O will be E squared, VE over Z cos beta minus delta minus V squared over Z cos beta. Now if we look at large machines, R tends to 0, and therefore beta tends to 90 degrees. Then our formulas become P developed is E V over X sine delta, as well as the output power. So therefore we can say that the losses is equal to the developed power minus the output power. And the same will go for Q. If we look at Q out, that'll be VE over X. Ay, little. That should have been sine. Sorry. Yeah. So VE over X sine 90 minus delta minus V squared over Z sine 90. So therefore the sine of 90 minus delta becomes cos delta. So we have VE over X cos delta minus V squared over X.